Our first presenter, Matthew Roberts. Matthew has worked with hydro governors and control systems for approximately 10 years. He has been directly involved in the design, construction, testing, and commissioning of dozens of digital governor systems ranging from 1 megawatt to 450 megawatts, including Francis, Kaplan, and multi-needle impulse and pump storage units. He's a member of both the IEEE Hydropower Subcommittee and the Western Electricity Coordinating Council Model Validation Workshop. Matt is currently Engineering and Operations Manager for American Governors. He earned his bachelor's in mechanical engineering from the George Washington University and has authored and presented numerous technical papers and articles. Matt was named one of the hydro industry's 30 emerging figures in the industry under 30 years old in international water, power, and dam construction 30 under 30 segment. So please join me in welcoming Matt Roberts.
Okay, so I'm going to talk a little bit about grid stability and what hydro's role in that is, and then particularly what hydro governor's role in that is. So, grid stability in the United States has been on a decline. What you see here are charts for, in the United States we have three grids. We have the Eastern Interconnect, the Western Interconnect, and Texas. And what you see is comparative. Within each region, the megawatt response for a 1/10 of a hertz deviation. And you can see a declining trend year after year in both the Eastern and the Western Interconnect. And there's not much data for Texas. So I'm going to talk a little about what a grid disturbance is and why it's important. So we operate at 60 hertz. And what does it mean when that changes? Well, you guys may know governors are responding to speed and controlling speed. Why are we looking at speed? Speed is a proxy of the balance between power generation and power consumption. The energy produced and the energy consumed at all times on the grid must match. If it doesn't match, that energy needs to either go somewhere or come from somewhere. So what you see up here on the top of the chart is a sample grid event. Let's say you have a large power generator unit tripping offline. So what you just have is you're going to have an immediate imbalance of power generation and power consumption. That energy needs to come from somewhere. The immediate source of that energy is from the inertia of the spinning equipment. So you see a decline in speed. So that's what we see that happens right away in less than the first second. So we have a decline in speed. Now all of your equipment that's supposed to respond knows that you have this imbalance and can start acting on it. So in your immediate response, starting, the governors are supposed to respond to speed disturbance within 0.2 of a second. So within 0.2 of a second, your governors are going to start responding. They're going to start giving out more power. And as this power comes online over the course of the first 5, 10, 15 seconds, you're in what's called the arresting period, where you start bringing that power balance back in the line and start getting to a point right at your bottom dip where your power produced and your power consumed match again. But you're still way off. You're now at 59.9 hertz. So the governors are going to continue bringing more power back on until they've given their drooped amount of response. We'll talk a little bit more about droop towards the end of the presentation. So at this point, you're in the rebounding period. You're still in, if you look at the bottom chart, what's called the primary frequency control. This is your governor response. The governors have now given everything they can under their governor response. So for a tenth of a hertz deviation, they're going to give a fixed amount of power up for that. And now you've settled back out at, say, 59.9 hertz. And this all occurs in the first 30 seconds or so of disturbance. What's going to happen next, and this is going to happen over the course of 20 or 30 minutes, is called secondary frequency control. This is your AGC systems, your automatic generation control, which is seeing the frequency deviation and changing set points. This is set point change. So all of the existing generation that's online is now being given a higher set point, or at least the generation that can accept a higher set point. And this is where you'll start seeing the frequency come back up towards 60 hertz in the recovery period. Now, if we just could ramp everything up and leave it there, we would have needed that generation on in the first place that tripped. So what needs to happen In the background is what's called tertiary frequency control. This is operator initiated, and this is bringing generation back online or online in the first place to replace the generation that had tripped offline. And over the course of what we see here is 15 to 20 minutes, going into 30 minutes, we're back to a state of where we started with replacement generation for the unit that tripped. So while this is a sample disturbance, this is a very typical disturbance. So who's contributing? Well, we know very well what kind of generation we have on our grid. Hydro makes up only about 6%. Most of it's coal. We have some nuclear, we have some natural gas. We know well who's out there and who's making power. What is complicated is who's doing what when things aren't going right. Who is responding to the frequency disturbances? Who is on its own giving primary frequency response, and who is acceptable? Who can accept secondary frequency response, set point changes, and also who can respond to tertiary control? Who can come online when required? So we're going to talk a little bit about the different types of generation that's online, and mostly focusing on what their function is and how their power production is scheduled and what their constraints are. So let's start with must-take power. This is your wind and your solar without storage. When the wind blows, we must take the power coming out of the windmills. When the wind stops blowing, we don't get more power out of them. We're kind of at the whim of when the wind blows and when the cloud and the sun shines. So that's kind of the overarching theme of what we're talking about here. You can see how as that increases, that can lead to instability. We have peak load. These are the units that come online to provide a peak load during peak times of the day or the season, and then come offline. These are mostly natural gas combustion units and some solar units as well that coincide with summer peak season. These can be dispatched. They're often very expensive to run, and they often run on efficiency limits and don't have very much primary frequency control. We have intermediate load and load following. This is really the focus of what we're talking about today. These are your hydropower, some of your solar with storage, your concentrated solar, and your natural gas combined cycle. These are your generation sources that do have the ability to control their output both instantaneously and on demand. And then finally, we have what makes up the base of our generation, our base load. This is our coal, our nuke, our big hydro that's non-modded, that's maybe run of river, that's not able to modulate its output to the same extent. Okay, so we've done some very basic modeling of this type of generation based on information we have of what type of units are contributing what type of response. And we know that the majority of response is coming from hydro and gas. And we've made some assumptions and some educated guesses at where that ratio between natural gas and hydro is. And what you see here is a chart of the percent of natural gas that's actually contributing versus how much hydro is contributing in percent of megawatts. And this really leads to a chart we have here, which is kind of the core of demonstrating hydro's contribution. What you see here is over a 30-second period, how much megawatts are being given by each source of power. And you'll see the two that stand out are yellow and blue, and that's your gas turbines and your hydropower. You'll see that while maybe the gas turbines are a little quicker to pick up the load, the hydropower is able to pick up a much more sustained load and a much larger load. So for every, we're here at HydroVision, we're interested in talking about hydro. For every 1% of hydro generation, of frequency responsive hydro generation we can add, we can get 0.5% improvement in our frequency control. So how can we do that? Well, we can add new hydro, but how often does that happen now? So we can improve, we can get more from our existing hydro. We can improve the responsiveness of our existing hydro. So how do we do that? We can implement frequency control on units that are less than 10 megawatts. right now, NERC does not require units less than 10 megawatts to respond to frequency. We can have improved governor maintenance. We can change out our governors, and we can tune our governors. Talk briefly about each of these. So currently, NERC does not require units less than 10 megawatts to contribute to primary frequency control. However, there are over 1,500 units in North America that are less than 10 megawatts. It's still more than 2 megawatts. And you can estimate that there's over 6,000 megawatts of generation that's not contributing to grid stability, that could be contributing to grid stability. That comes out to 4% more of the current hydro generation. So a 4% increase in frequency response capacity could result in a roughly 2% increase of primary frequency response. And while the numbers maybe don't look that big, it's a cumulative effect of all generation adding in and responding, especially during that resting period. Okay, governor maintenance. So, how many people here have received the NERC governor survey? Okay, I guess we don't have any utilities here, or you guys have. Okay. That'll lead into a few things I'm talking about. NERC is going out and asking utilities about how their governors are operating and how their governors are maintained and what their settings are at. And they're trying to collect this data to help figure out what's going on in the grid, why we have this decline in performance. And part of that is in the deterioration of the response of existing governor equipment. So signs of this are if you have a mechanical governor that you have trouble synchronizing or is unstable when you're online, then if it's unstable just at steady state, you can't imagine how it's going to respond when you actually have a disturbance going on. So this leads to instability caused by lack of response from the governor systems. It also causes instability from unplanned outages from governor systems that cause outages, and from extended outages where we're now taking hydro offline, which is, as we can see, a major contributor. Additionally, there's some snowballing effect where if you have unstable grid, you have more operation of your governor, which increases the wear, and as you increase the wear, you, as we just said, can increase the instability. So, we'll be the first to tell you that mechanical governors can control the grid as well as any type of governor out there, analog, digital, if they're well maintained and if they're well tuned. Now, it's getting harder and harder to maintain these units. The expertise is going away. The desire to have the plants staffed. We used to have plants that not only had an operator there, but they had a full maintenance crew there, electrician there, and people to oil everything every day. Now you're lucky if someone drives by once a day to make sure the gate's still locked. So you have, when you switch to a governor, like a digital governor, you have fewer hardware components that can wear. You have essentially more reliable long-term performance. Your software is not going to wear out. Once you set your gains, that's where it'll stay. Additionally, you have improved governor interface to your larger control systems. So you can have direct set point entry from your AGC system. We did a project in California where we have Cal ISO sending us set points directly into a governor. I did a paper on this last year at Stanislaus, 100 megawatt unit, 60 ohm impulse unit, ramps up and down from nearly 0 to 100 about 100 times a day. And it's Cal ISO directly sending the set point over a DMP communication link, and we can just follow them up and down like a yo-yo all day as they want. And so this leads directly into improved secondary and tertiary control from better control of your governor system. And what I finally want to talk about is tuning. And this was kind of going back to the NERC questionnaire that I was referencing. Is, governor systems are not that well tuned. They're set up for stability. So what's your definition of stability? Well, it can synchronize easily, and then when it's online, of course it's stable. The grid's 60 hertz. It's not moving much. Well, that's not really the case. You're tuning your system for this one particular condition where you have an isolated unit spinning by itself. The values you put in for your gain adjustments for, let's say, your PID controller or your temporary droop gains on a mechanical governor have very little bearing on how it's going to operate when you're connected to an infinite bus with transmission issues and different water starting times. Because now your gates are full open. So a lot of what NERD is trying to do, and WEC particularly in the model validation work group, is see how these units are responding and try to get some guidance on how to tune them. And that really falls into two areas. Permanent compensation, which you guys know is droop, and temporary compensation, which mechanical is often referred to as a temporary droop, or in a digital control you call your PID control. So your permanent droop is how much you're going to respond to a frequency deviation. When you saw that the governors respond during that primary response, how much were they going to respond? Now, this is only required for units over 10 megawatts. It's typically set at 5%. But saying 5% across the board for everyone, that's not optimized for how we need to control it. There are certain ECCs and ISOs that will say you need to run at 4% droop, you need to run at some other droop. But typically, that's not getting the attention it deserves. Additionally, your temporary compensation is how you get from when you're at 60 hertz to where you're sitting when you're at 59.9 hertz. Do you ramp it very quickly? Do you ramp it slowly? And how that plays into the overall stability of a disturbance. Now, as I said just a minute ago, most of the units are tuned for offline response and offline stability, and that isn't very applicable to online stability. So hopefully as the models are made better and responses are coming in from utilities, the WEC and the ISOs can start making recommendations on tuning, and we can start seeing some improvement in how the governors respond to the disturbances. Any questions?
Right, we do have time for a couple of questions for Matt. In the audience, I do have a question.
Okay.
We own a bunch of hydro units in California, and governor tuning is a very important part to provide frequency response. You work with utilities all over US and Canada. How often do you find units which are tuned improperly?
I think most of them are.
Yeah.
We very, very rarely work with a utility that will even look at what we're doing when we tune units. Now, so I'm not saying we tune them poorly, but we tune them for offline stability, which is the only thing we can tune for. I can't go and do a step response and make the unit go to 60.1 hertz. That's the only government response to that. The only way to tune for that stuff is through modeling.
Right.
Now, we are seeing, we do a lot of work with the Corps of Engineers, and they work closely with BPA, and BPA has taken a huge interest in this. And they have given us probably the best direction we've seen from anybody on what our online responses can be. And we've seen running gains that are much more aggressive than we would normally put in, because we now have some direction of what we're looking for. And that still is even in question. If anyone here does go to any of the model validating work group meetings, you know that there's question on everything. And every time they sit down and meet, they have some different ideas of how to respond to this. So I think that the entire area of tuning is very much in flux right now. All right, back.
I referred to your chart where you compared the different technologies regarding speed response, exactly that one. I'm surprised to see that gas turbines are shown as being faster than hydro. Maybe this includes the startup time from standstill. But if you, what is a trend, that hydro is run at very low power or even at speed no load, and then is used to ramp up for stability reasons. Hydro would be faster than gas turbines. Can you comment on that?
Yeah, well, I think this was, these are rough generalizations, and these are more for load changes once at load. I think you make an excellent point, though, that hydro is unique in its ability to have fast startup and in its ability to run spinning reserve. We work with a Southern company in lower United States, Alabama, Georgia region, and they take their units offline once a year. And when they're not generating, they go into spinning reserve. So they can take a unit from making no power to full power in 30 seconds. And I don't think any other source of energy can do that. And even from a standstill, it's not uncommon to see a unit go from no power to full power in 2, 3, 4 minutes. So, and that is one area where digital controllers, not just on the governor, but in the whole unit control scheme, can improve responsiveness, is taking a unit from a dead stop to online. You can synchronize faster, you can run through your feedbacks faster, you get rid of some of the timers and have active feedback of your sequence of starting. All right, thank you.